Konstantin. And
This meeting is being recorded.
do you pronounce that Batygin?
Oh, it's been pronounced, every which way possible and more. So it's Batygin. It's usually, originally pronounced Batygin, but I will respond to anything, including Chad.
Oh, okay. Well, this is Dr. Konstantin Batygin, and I saw him last month's meeting at the Tri-Valley Club, and I found the discussion deep, highly fascinating. And as usual, it left me with a few more questions that I had before, but I know a few things about this talk, so I have to keep it to myself and ask later if they don't get asked. But it's quite amazing how he's come up with the evidence that there is a massive ninth body lurking out beyond Neptune. And he'll be showing us the reasoning behind all this. His bachelor's in sciences of physics was from UC Santa Cruz in 2008. And I know we see UC Santa Cruz astronomers on NOVA all the time. His graduate studies were at Caltech, which, that's a whole different strata of science there. He was a postdoc scholar at, and I'm going to give this the best shot I can, Observatoire de la Côte d'Azur in Nice, France.
Yeah.
Oh,
you got it.
Yeah.
You got it, yeah.
And also at Harvard University. And he's now on staff at Caltech. And possibly the most interesting thing going is he's a singer and guitarist for the rock band The Seventh Season, which I'm pretty sure he's going to play some songs for us tonight. So, ladies and gentlemen, Planet 9 from outer space, Dr. Konstantin Batygin.
All right. Thanks very much, Jeff. Really appreciate the intro. I did not prepare any music for tonight. You're welcome. So let's get going, talking a little bit about the outer solar system. So this is, of course, not just work that I am interested in solely, not work that I've been doing exclusively by myself. I have a bunch of partners in crime who are all, having fun along with me, and their names are listed here on the bottom of the slide: Mike Brown, Alessandro Morbidelli, David Nisworny, Rosemary Mardling. So I want to really spend today's discussion just kind of giving you guys a bit of an update of where we are with the Planet 9 hypothesis. And I think a good place to begin is to take ourselves back, 30 years, I guess now closer to maybe even 40 years ago these days, to what we thought the solar system looked like, right? This is the solar system top-down view. You've got Mercury, Venus, Earth, and Mars. The pink circles are Jupiter, Saturn, Uranus, and Neptune. And this blue ellipse is the orbit of Pluto, which was mistaken for a planet initially, right? Back in 1930, upon its discovery, it was considered to be a one Earth mass object. Turns out it's not. Turns out it's 500 times less massive than the Earth. And it's as it turns out, Pluto is just a particularly massive body within the second belt of asteroids, icy asteroids, that lives beyond the orbit of Neptune, right? A lot of people are familiar, of course, with the asteroid belt itself, which lives between Mars and Jupiter. And as it turns out, the solar system has a whole other reservoir of icy bodies, a much more massive reservoir of icy bodies that chills outside of Neptune and kind of does its thing and orbits. The discovery of this field of icy debris is relatively new, right? Pluto was the first object discovered in 1930. The second one was discovered by Jane Liu and Dave Jewett only in the early 1990s. And since then, the discoveries of the census of Kuiper Belt objects has really skyrocketed. So now we know of sort of thousands of KBOs. It's actually kind of interesting. The census of Kuiper Belt objects and the census of extrasolar planets have been roughly gone hand in hand, and their discoveries have roughly gone hand in hand as well. So the mere discovery of this field of icy debris and mapping out its dynamical structure immediately told us that our story of how the solar system formed was in trouble. Because prior to really the mapping out of the Kuiper belt, this field of the second icy asteroid belt, it was thought that the planets simply formed where they are today. That sounds like a pretty good, leading order assumption, but the dynamical structure of the Kuiper belt, the mere presence of the Kuiper belt tells you that that's not the case. And over the last really a decade and a half, the evolution story of the solar system, right, the early evolution story, has been rewritten in favor of a scenario where, in fact, the giant planets, Jupiter, Saturn, Uranus, and Neptune, start out much closer to the sun and are initially encircled by a field of icy debris totaling about 20 Earth masses. And within the first kind of few tens of millions of years of the solar system's lifetime, the giant planets kind of make their way through this field of debris and temporarily go unstable and scatter their orbits. And so upon recircularizing through dynamical friction, right, these planets end up where they are today, and the remainder of these icy debris getting flung out is what we today see as the Kuiper belt. Okay, and so what I'm showing you here is, of course, a movie of the solar system's early evolution, but it's not just a movie. Didn't have a script. The script was written by a calculation. This is an outcome of one of these instability-driven models that all are collectively called the Nice model, because the first really coherent set of models came from the Nice Observatory. So that's pretty cool. Okay, so the discovery of the Kuiper belt really had this important effect on rewriting the solar system's early history. What's important, though, is that once you have this realization that the giant planets had this temporary period of instability, everything else falls into place. There's nothing about the Kuiper belt that kind of doesn't make sense in the leading order way, until you look far enough. And this was really the starting point of this whole Planet Nine story, is when my partner in crime, Mike Brown, and I, we were inspired by work done by Trujillo and Shepard, who found one of these objects. And what we noticed is that if you concentrate on the most distant orbits that exist in the solar system, that we know of in the solar system, there's an interesting pattern that emerges that you can actually just see by eye. You don't need to be a great statistician. You can see that, by kind of just turning around these, or they're all tilted with respect to the plane of the solar system by sort of 10, 20 degrees, and they're all pointing to the left. Okay, so what's going on, right? Why is this happening? So, of course, the first reaction you might have looking at the previous slide is, well, you've got 6 orbits, maybe that's by chance, maybe there's a coincidence. These days, the data set is much more, it has sort of expanded by a factor of 3, it's much more rich in distant Kuiper belt objects. And as it turns out, this pattern of orbital clustering is not only there more broadly, it correlates strongly with the orbital stability of the Kuiper belt objects. So this is going to be really important. We'll come back to this again later. But again, this is now the 2021 census of distant KBOs, where I have kind of labeled each of the orbits by what happens to them if you just let them go. And the green ones are the ones that interact with Neptune very strongly and chaotically diffuse. Their orbits are kind of on their way out of the solar system. And the purple ones are the ones that are dynamically stable. Okay? These are the objects where if you let them go, nothing happens to their orbits. Okay? By the way, if at any point you feel like something is not making sense, or you have a question, please don't hesitate to just interrupt me. There's no need at all to hold questions until the very end, I want this to be more of a discussion than, you know, me just kind of talking for a while. So again, you will not hurt my feelings if you interrupt me. Okay, so this, as it turns out, this pattern of orbital clustering, right, in the outer solar system, at least if you just take the data set at face value, it's really there. Right? So the next question becomes, why is it there? Why should the outer solar system exhibit this pattern of orbits facing preferentially a common direction? And a typical answer in solar system dynamics, if you find anything interesting, is, well, something bad must have happened 4.5 billion years ago to the sun, and that's why, you know, you still see this relic. But as it turns out, that doesn't work. So that explanation for the outer solar system fails, because if you were to let all of these objects go, just wait for a few 100 million years, which is a relatively short time compared to the lifetime of the solar system, because these orbits are all different sizes, they would precess out of alignment. So indeed, if you interpret the data, okay, of what's happening in the outer solar system as just being indicative of what is really out there, there's some gravitational restoring torque, which is keeping these orbits confined, keeping them all clustered together. So what can it be? Well, in fact, it can really be anything, but it has to have the qualifications of having a mass on the order of a few Earth masses, and it has to orbit the solar system, right? And exert this perpetual, restoring gravitational torque on an orbit that takes about 10,000 years to go around the sun, and is appreciably eccentric, appreciably out of round. This is a movie, again, of one calculation that we've done. Okay, we've done probably tens of thousands of them at this point, but this is one particular one which that I like to show, which shows, you know, the long-term 4.5 billion year evolution of the solar system modeled, where you've got Uranus and Neptune here as these pink circles, the orbit of this mysterious perturber as the large pink ellipse. There's an object of about 5 Earth masses, and the orbits that you see dancing around everywhere are the modeled orbits of distant Kuiper belt objects, where the blue orbits are the ones that are sufficiently long enough period, right, sufficiently distant to really strongly interact with this perturber, to which we will refer to as Planet 9, because I don't know much, but, you know, things that tend to have masses on the order of a few Earth masses tend to be planets almost always. Now, you might ask why this pattern is emerging, right? Why this clustering is appearing in the solar system. And the answer turns out to be this interesting interplay between Planet 9 itself and Neptune, right? As Planet 9 causes these orbits to dance around and precess all the way around azimuthally, the orbits actually experience a maximum in their eccentricity, a maximum in their ellipticity when they are aligned with the orbit of Planet 9. What happens during this maximum of ellipticity is that the perihelion, the closest approach to the sun, gets jammed into the orbit of Neptune, and Neptune ejects them. So this emergence of a pattern of clustered orbits, right, correlates, so it naturally kind of singles out orbits that are dynamically stable, that are comparably low eccentricity, if you will. So you can do these types of calculations. They're relatively straightforward to do these days. You know, it's not something that requires you to be, you know, even remotely competent, and they're fun to do. one of the other things that I'll draw your attention to is the fact that there's this one thing that's coming out of the plane of the solar system at the very end, and we'll come back to that as well. So again, the idea here is that if we interpret what we see in the outer solar system at face value, then a perfectly plausible explanation, and in fact, the only plausible explanation for the pattern that we see is that there's some other gravitational thing that is keeping the orbits confined. Okay? So, okay, that's kind of where we were in 2016, 2017. We said, see this pattern, if there's no external source of gravity, it would disperse over a geologically short time. So we need a source of gravity. Turns out the kind of gravity we need is that of a planet. There could be a planet, okay? And of course, immediately you have to stop and say, but wait, you know, are we deluding ourselves? Because is this pattern that we're basing the story on even real? And this has been a question that's lingered really in the literature ever since 2016. There have been multiple papers published upon discussing the observational biases inherent to the outer solar system, you know, arguing for or against the statistical significance of this pattern of clustering. So the answer, well, you can obtain, first of all, before we get to the answer, you know, prior to last time I gave this talk, I guess 3 weeks ago, I did a quick search on the internet, okay, on twitter.com, right, which is where you go to get your latest, you know, hot take on anything outrageous. And I think the consensus on twitter.com is clear, right? Like, blah, 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 evidence for Planet 9 does not exist. It's not there. Planet 9 is dead. Don't let Avi Loeb overshadow the fact that Planet 9 is dead, etc. Planet 9 postdoctoral researcher appears and says the woke are getting more woke. Okay, so you know, really a lot of information on this website. So what is like, what's going on? Well, in order to answer the question on of whether or not this pattern is statistically significant, you can really take one of two approaches. Okay, you can either do what's called survey simulation, and doing survey simulators ultimately boils down to taking the observational footprint of a given survey, right, and saying, where did you look? And if you only looked over there, all of the Earth's objects in the distant solar system were all discovered by the same survey, of course you would have them be clustered together because you only looked over there, right? So you can only discover orbits that are aligned in a particular way. That's the basic idea. Now, as it turns out, the distant solar system is composed, the census is composed of orbits that come from about a dozen different observational surveys, which all have their own observational strategies, their own biases, their own sensitivities. So it's very difficult to convolve all of that together. So what usually people do is they throw away the part of the data that doesn't come from very well characterized surveys and just look at a subset that comes from surveys that have very well quantified biases. And that can be either because there's only one spot in the sky where they point, you know? And so beam surveys like OSOS, or you know, they have a very well quantified survey coverage like the DES survey. So if you do this approach of asking, can I distinguish based upon what I see, and with this, you know, subset of objects that come from well quantified surveys, the answer is always no. You don't have enough statistical power to say anything, really. You can't tell if they're clustered, you can't tell if they're unclustered. You can't tell if they have some other pattern. There's just not enough data there to make the distinction, because you're dealing with only a handful of objects. This is maybe not profound, right? If you want to, I don't know, have a statistically significant sample, it helps to have more than 10 data points, right? I think this is something that people in high school know. But then, given that this survey simulation approach fails, you can resort to a different fact. And this different fact is the notion that, well, at the end of the day, the distant Kuiper belt is not 14 bodies, right? The Kuiper belt is thousands of bodies, right? We know of thousands of objects in the outer solar system. And the process by which we discover them has nothing at all to do with their orbit. In fact, for the first year, you can't tell anything about the orbit. Okay? All you know for the first year is where the object is on the night sky and how far away is it from the sun, which for all of these objects is roughly the same. So the other thing you can do is to do what I like to call observability mapping, which is to say, okay, we have a distribution of discoveries on the night sky. Okay? There's information there, right? That distribution of discoveries actually kind of tells you where people have looked for Kuiper belt objects, okay? Because that's where they've been discovered. And then you can do the exercise of saying, given all of these discoveries that have been made, what are the chances that we have found all the distant ones clustered together in this particular way? And of course, I'm simplifying this a lot, but the basic idea is that. And the answer is there's a perfectly good and well-characterized chance that all of this is false, okay? That this pattern of clustering that we see in the distant solar system does not really exist. And the false alarm probability is 0.4%, okay? So that I am saying there is a chance, okay? So there's a 0.4% chance that anything that I say in this talk, you can just forget and, or, make fun of me a posteriori. Whatever you want to do with this information is up to you. But, the kind of glass 99.6% full way of looking at the data set is that ultimately what the data are telling us is that this pattern of clustering really is real. And I like this plot, which shows the kind of azimuthal offset with respect to planet 9 of objects in the simulation, which is the background red color that you see. And if you go back a couple slides, you may have noticed that all the stable orbits at the end of the simulations were kind of anti-aligned with respect to the orbit of planet 9. That's why there's a red streak at 180 degrees as a function of the semi-major axis, how big the orbit is. And the green points are the observational data. These are the stable objects. And each one is also characterized by a strip, a vertical strip, where the color code, the blue kind of, the lightness of the blue tells you where these objects should have been discovered statistically if they were just discovered through observational, like if the entire thing was just observational bias. And again, you can do fancy statistics, but you really don't have to. You can just look at this by eye and convince yourself that, well, the data are at the very least appearing at the overlap point between where the model tells them to be and where the observational strategies allow them to be discovered.
Question?
So, yes.
Question? So you said I could interrupt, right?
Sorry?
You said it's okay to just blurt out and interrupt, right?
Yeah, of course. Yeah.
Okay, so on this is delta omega. Is this the omega that's the longitude of perihelion?
Yes, sir. Yeah, this is the longitude of perihelion.
What we're looking at is the differences in the longitude and perihelion, and it's showing that they're all kind of lined up the same way.
Correct. Yeah.
Okay.
This is just the orbital element way of saying that in the simulation, all the stable objects are anti-aligned with respect to orbit of planet 9, right? And if you look at the data, subtract off where we think planet 9's longitude of perihelion is, right? The orbits, well, they fall kind of by definition there. But if you then ask the other question of how likely are these objects to have been discovered where they are, if it wasn't for planet 9, the answer is only 0.4%. They should have been discovered lower with a delta of RP of closer to 90 degrees and closer to about 300 degrees. That's where the two kind of blocks are. Instead, they cluster around 180 degrees. Does that make sense?
Yeah, I just want to make sure I was reading the graph correctly. But yeah,
no, you got it.
Okay, it's just amazing that they're all lined up, pointing out the same way like that.
It's a police lineup of the outer solar system. The amazing thing also, like, I bring up this question of bias, both because there's been quite a bit of attention dedicated to it, but also because it's important. Ultimately, right, if any theoretical story is only as good as the data on which it sits, right? So I think it's really important to do a good job and answer this question of bias in a statistically rigorous way. And in this case, it turns out to be that it really works out. And importantly, the signal, over the last 6 years has gotten stronger, not weaker. And we've really realized this. We kind of suspected this correlation with orbital stability even back in 2016, but that correlation has really appeared in the data, which is really important, again, because the only way to generate a correlation between orbital alignment and orbital stability is through interaction with some gravitational body, right? You can't do it any other way. So it's pretty cool. Okay, so I want to now come back a little bit to this, the end of this simulation, right? Where, I showed you, and I asked you guys to pay attention to the fact that there's this out of plane object that is appearing, right? And I've asked you to keep that in mind. So this is something that always happens in these Planet 9 simulations. So if you successfully cluster the orbits that are in the plane of the solar system, right? These guys that are kind of doing this, then you always also get these out of plane objects. And we thought this could be, a pretty cool prediction, right? That if you go and look for highly inclined objects in the outer solar system, you will find them if Planet 9 is really there. So it turns out it didn't take us very long at all to find them, because they had already been discovered by the WISE mission, and they were kind of sitting in archival data. So just by looking at the list of discoveries of the WISE mission, we noticed that turns out there's this whole population of bodies that are about 90 degrees off from the main cluster that orbit the sun in a perpendicular manner to the plane of the solar system. So this is quite interesting. We've spent a little bit of time really trying to understand the origin of this dynamic, how this comes out. I don't want to spend any time actually talking about mathematics, other than to say that this is a octopolar effect, which is like an octopolar high inclination relative of the same dynamic that generates the clustering in the plane. And I want to highlight the work done by my former student, Juliette Becker. She's now my postdoc, again at Caltech, but she, using DES data set, found one of these high inclination bodies that are actually in a process coming out of the plane and evolving to become a highly inclined object called 2015 BP519. All of these names are, extraordinarily creative, right? And so, this pattern of highly inclined objects, which do not really ensue naturally in the solar system, is yet another hint that something interesting, something gravitationally interesting is going on in the outer solar system. So if you follow the thread of these highly inclined objects, yet another line of evidence appears. Okay, and so again, I want to show you a numerical simulation. This is Uranus, Neptune, and this is the orbit of planet 9. This yellow thing here is just a KBO, right, in our simulation, and if we let it go, right, what it's doing is it's dancing, it's going through these chaotic orbital flips. Its inclination is going from being in the plane of the solar system or perpendicular to the plane. And every time the orbit hugs the orbit of Neptune, it gets the chance of being either scattered out of the solar system completely or scattered inwards. Okay? And a few years ago, we spent a bit of time trying to understand what happens to the objects that are scattered inwards. As it turns out, there's this dynamical pathway wherein objects from the outer solar system, things that take 10, 20,000 years to go around the sun, once actually get re-injected back in to the solar system if planet 9 is there, and they do so at very high orbital inclinations. Yeah? So planet 9 is really there. It's polluting the outer solar, the interplanetary space between Jupiter and Neptune with highly inclined objects, things that are called centaurs. And again, if you look in the data set, turns out these objects really are there. Okay, so in the background, the kind of 2D histogram that we see here in green is where the objects go in the simulations. Okay, and the black dots with the blue kind of halo are real discoveries, real objects, real Kuiper belt objects with inclinations greater than 60 degrees. Importantly, there is no way for a regular Kuiper belt object to attain an inclination greater than 60 degrees just through interaction with Neptune. Okay, it is not something that ensues ever. Okay, so these objects require an external gravitational potential to perturb them. And people have looked into the question of whether galactic tide and passing stars are enough, and the answer is no. In order to reproduce the flux of these highly inclined objects that are polluting the kind of Jovian to Neptunian space, you need something like planet 9. Actually, if you use the planet 9 mass and orbit that we kind of proposed in 2019, you get the flux perfectly. This is not my determination. This was done by Nate Cabe at University of Oklahoma. Okay, so with all of this in hand, one might be in a situation where say, okay, you claim that you're able to explain the common tilt of the distant Kuiper belt, the fact that they all cluster together in longitude of perihelion, the azimuthal orientation of the orbits. Like there's this population of highly inclined distant things that the models predict that really are there. There's this pollution of highly inclined centaurs for the outer solar system that also are there. So if you know all this, like, what's the big deal, right? Why do you refuse to go and find planet 9? Why do you keep looking down at the computer instead of looking up and just like going and find it? And there's this other lesser known Institute of Technology on the East Coast that I think summarized the reason well, is that given the level of detail, it's easy to imagine that we can just point to an area of the sky and look there, but it's not the case. And the reason it's not the case is that we don't know where planet 9 is on its orbit. We can sort of calculate the mass and the orbital elements, we cannot calculate where it is on orbital elements. And the reason we cannot calculate where it is basically because we haven't seen the KBOs go around the sun once. Now, I plan to live on as a, artificial super intelligence for the next 20,000 years. So I will get the opportunity to observe them as they go around the sun once. But so far, the arc that we have in the data is on the order of 10 years, which is 1/1000th of the orbit. So if all you know about the KBOs are the orbits, and you don't know, how their orbits change, that minuscule change over a single orbital period, you cannot compute where planet 9 is. It's, from a dynamics point of view, it's where it is on its orbit is just determined by Kepler's second law. So that's why we haven't found it yet. Also, the other reason is that clouds are getting in the way. And I used to be just a purely simple theorist. Now I'm just a simple theorist with a little bit more observational experience. And it was staggering to me because I used to think, okay, what's the big deal? Like, come on, go get some data. It seems pretty straightforward, right? You just point a telescope at the sky, take a picture, come back the next day, take the same picture, come back the third day, take the same picture. And getting really involved in the observational process of looking for Planet 9, what I've realized is that this is a highly inefficient process, especially because where Planet 9 is most likely to be is kind of close to the intersection of the ecliptic and the galactic plane. And the galactic plane gets in the way. I hate the galaxy. It's got too many stars in it, right? Which are preventing us from doing good observations for Planet 9. The other thing that's troublesome is that all of this is, ripe for observing in December. And December, November, and January on top of Mauna Kea is bad conditions. Even though Mauna Kea is great conditions overall, right? We have been, I think we have had about 80% of our observing time be destroyed by weather alone. So it's been an interesting and illuminating experience. Now, this is not to say that there's no hope at all, right? We're determining, and a group in France, led by Agnès Fienga, has actually used spacecraft telemetry to try and put constraints on where Planet 9 can and cannot be on the night sky. Unfortunately, this exercise has fallen short of detection, but it does provide some useful constraints, which is pretty okay. I think that a good place to stop would be here, because the story has evolved a little bit beyond this, but only in a technical sense. We have been doing calculations to understand if the inner Oort cloud, which is a even further population of Kuiper Belt objects, meaningfully interacts with meaningfully alters the Planet 9 story at all. And it does on a quantitative level, but really qualitatively, everything that you've heard today is a summary of kind of the state of the art. So again, to summarize the lines of evidence, we really have four reasons why we believe that Planet 9 is there. One is the clustering of the orbits. The other is the common tilting of the orbits. The third is the excitement of these long period KBOs. And the fourth is the fact that Planet 9 is expected to pollute the Jupiter to Neptune space with called centaurs, icy bodies that are coming in from without, and we really do see that. And there are a couple of caveats for the estimates of Planet 9's eccentricity, but I think for the purposes of this talk, they're not particularly interesting. So I would like to stop here and take any questions. Thank you.
Yeah, this is really awesome, Doctor. I do have a couple of comments.
Okay.
You spoke at the other group about how if it were like a trans-Neptunian object or Kuiper belt object of material, be methanes, ammonias, and ices, and possibly be a certain size, and because of that, a certain reflectivity, a certain
Yeah.
brightness. Can you expand on that a little bit?
Yeah. So, if we are ultimately all in California, right? So it's important to be fueled by maximum amounts of enthusiasm, right? And if we are enthusiastic, then we can imagine that Planet Nine has a composition like, sort of like a scaled down Neptune, so an icy core with some hydrogen and helium, and work done by Jonathan Fortney and company at UCSC basically suggests that if you take such an atmosphere and put it at a very, very cold temperature, then then what you will get is all the stuff that can condense out will condense out, and the atmosphere will become a pure Rayleigh scatterer, and because of that, it will become highly, highly reflective, meaning albedo of 60-70%. Okay, that's the optimistic view that we actually adopt in whenever we make estimates of how bright Planet Nine is. We say, okay, if this is true, it's magnitude sort of 23, 24. Right? The other view we can take is that maybe Planet Nine doesn't have a appreciable hydrogen helium atmosphere. Maybe it's like a Pluto, right? Scaled up Pluto, and then we will find it. I don't know, not in 2023 when the Vera Rubin telescope goes online, but in like 22, 23. Well, maybe a little sooner than that, but yeah, we don't know what it's made out of, right? It could be a hamburger, it could be a burrito. As long as it's 5 Earth mass, it's going to do the job.
So the other thing I asked you about at the other meeting that I don't know if you're interested in talking about now is we have read that a possibility of a baseball-sized black hole orbiting out there. And so my question last time was, how is a baseball-sized black hole even made? So I know the answer, but I thought maybe the other people would be interested in that.
Yeah. No, so it's a good question. The answer is there's no way to make a baseball-sized 5 Earth mass black hole through just stellar evolution. You have to make it through a different pathway. The kind of pathway that people like to quote is that these could be primordial, what are called primordial black holes. During the Big Bang, you can generate a whole spectrum of black hole masses, and the smallest ones evaporate through Hawking radiation, but ones that are more massive than sort of the biggest asteroids are supposed to still be around. No one's ever seen them. Doesn't mean they're not there, but I would say that the black hole story is far more speculative than the Planet Nine story, because if the sun has a binary companion, which is a primordial black hole, that insinuates, just statistically speaking, the number density of such black holes to be very, very high. And I think that there are results from the search for machos, which are massive. There was a candidate for dark matter back in the day, which kind of through lensing do not necessarily rule out the possibility that Planet Nine could be this black hole, but they basically suggested it would be highly, highly unlikely. Does that make sense?
Yeah, I've never really knew there were such small black holes, or if they really are. The other thing is, I know that one method of looking for trans-Neptunian objects is to stare at Sagittarius for long periods of time and wait for stars to blink out and blink back. But trans-Neptunian objects are generally small, where this object would be like huge compared to all these other objects. So maybe a blink out of a star is a highly more likely event with something like that.
Right. So, occultation, once we know where Planet Nine is, then occultations will be cool to do. It's not a good way to. I think occultations are not like a good way to discover this object and then measure its orbital parameters, right? Occultations are good if you want to measure the shape of a Kuiper belt object that you already know is there. Yeah, especially if it's close to the galactic plane, there'll be a ton of occultations, but that's not a good strategy to discover. I must give a brief warning. My computer tells me that it has 2% left in its battery, so we will keep going as long as we can, but it might not be that long. I paid a lot of money for this battery, so I expect it to last a long time, but we'll see. So yeah, the best way to really just look for Planet 9 is to just do the standard, bread and butter thing of take a picture, come back the next day, take another picture, come back the next day, take another picture, and look for things that move, right? And if you have, because you get the parallactic distance right away, if you can see it and it's at 500 AU or whatever, it's Planet 9. There is no other possibility. You cannot confuse it with something, because if you've detected it at 500 AU, if it's magnitude 24 or 25 or whatever, it's not a KBO. It's a thing that's 3 Earth radii.
Does anybody else have any questions?
Hey, it's Eric. I have a question.
Yes,
Do you think that there could be any data from the Voyager spacecrafts that would hint at any sort of perturbations in its motion as they were traveling outside the solar system?
Not from Voyagers, but from Cassini, yes, because Cassini telemetry is very good, and Cassini has, really it's orbit of Saturn. It's not Cassini itself, but Cassini, right? And this is what the Fienga and company have tried to do, is to determine the tidal perturbation upon the orbit of Saturn, and it leads to interesting constraints, but not detection. And for this, the other spacecraft are all pretty useless. And this is what, again, my colleagues in France have looked at this. The other one that's kind of mildly useful is Juno, but even that is not, it's just the baseline is not long enough.
Yeah. Okay, thank you.
Okay, I am now.
Sorry,
I'm now at 0%. So I want to preemptively say thank you all for logging on and watching my my talk. I really appreciate the time. I appreciate the invitation.
Thank you.
And hopefully we can do this again at some point in 3 dimensions. Yeah.
We will ask you again. And so you're at the airport?
Yeah, I'm at the airport.
Wow.
Yeah. I'm always at the airport.
Okay.
So why not?
You didn't get mugged. We're impressed. Yeah. Thank you, Dr. Batygin.
Thank you very much. This is
All
highly
right.
fascinating.
Thanks very much. All right. Bye-bye.
Very good.
Okay, Mikey, you're on.
Sure.
I do have a winner. In case
Okay, I'm not muted.
you're on.
Oh, okay. All right. Well, that was a lot of fun.
Yeah.
That was good. Ordinarily, we would be in a restaurant right now and some people drinking, others finishing up their meal. Obviously, that's not happening. So I just thought I'd take a little survey here to see what everyone's had for dinner tonight. I was even listening to Dr. Batygin. Jerry, let's start with you. You've always got a glass of wine in your hand.
I
What
know. I'm a teetotaler tonight.
Oh, I'm really disappointed. Anyone else want to volunteer?
And we had dinner before the meeting.
Okay. Yeah, I had chicken tacos tonight, so I was happy about that.
Very nice.
Does a good job. Anyone else want to volunteer on? No one ate anything, I guess. Good for them.
No, I have
Dungeness crab.
Now I'm jealous.
I
Anyone
have
going to
very
grab
good
this
chile.
year? We were signed up for 1 crab feed. Nothing, huh?
I just had some brisket and beans is what I had.
Okay, well, sounds like
A
we're all-
nice salad and a bowl of nice soup.
All right, do we still have Doug? Was Doug able to get through?
Doug never came back.
Oh, he messaged me and said that his same usual connection problem happened and he's gone.
Yeah.
Too bad.
Well, anyway, Gary, you mentioned about the Oak Park star thing that we had on the weekend, and actually it was pretty nice. We didn't have much of a turnout, but the weather was decent. Had a good time talking and catching up on things, and hopefully next month there'll be a little bit more activity coming in. What happened then was rather unusual, but it was still a nice evening for all of us. So.
I like Bob Jarrett's picture because around his head are gravitationally lensed galaxies around.
Is his head distorted?
It is.
Oh, completely.
We have a winner every week or every month. Mike gets a Starbucks card, and we did a raffle. And I'm going to mispronounce his name. I'm sorry, but is it Zhuang Ngo?
Yes.
Is that how it's pronounced?
We need an address.
Swan, like a swan.
Oh, okay, Swan. No, okay. You are the winner of a Starbucks card. Do you like Starbucks?
Why am I the winner? I don't get the
We do
rule.
a raffle. If you
Everybody-
attend the meeting, you're eligible to win a Starbucks card.
And so what happens is he gets the card. Then when people are in, I write down their names. And then I throw this die that I got from the Sophia mission. And I whittle it down until one winner wins. And you are the winner.
Right,
Really?
you're right.
How can I get it?
Here's how you're going to get it.
Meet us in back of Mo's bar in the alley.
You'll have to email me your address and I'll mail it to you.
Oh,
you're
that's
comfortable doing
sweet.
that? Are you comfortable doing that?
I don't have any information. Maybe Dr. Jerry or someone can
Okay, I'll give it to you, Jerry.
like.
Can you, let's see.
Can you get me your email, because I get this program through my
Oh, okay.
professor, Dr. Hedrick. So
I am still, I'll do a message here.
Okay, so
In
Jerry, I think
the
it's your
dark.
card.
at gmail.com.
I wish we could be in a group with, I see who she is.
You know, that'll go full screen too.
Oh,
That picture will go full screen.
I'm so lucky.
that's
I hit
okay
that view up
because
there.
It's the first time I joined the group too.
Yeah, Jim,
Jerry,
would that,
I'm gonna get you the
a
card and then
group,
you
would
get
that
her.
still show?
Yeah.
Oh,
yeah, that'll work.
Okay,
Yeah,
So,
yeah. Jim Hetrick
Lauren-
gave her our address.
just by
I'll
hitting
go-
that
Yeah,
right
the
there?
view,
I'll give this to Professor Height and then he'll get it to you.
There you go.
Congratulations.
doing that.
Thank you.
Speaker,
All
whatever.
right.
Yeah, Jim Hetrick. Xuan is an astrophysicist who switched to data science.
Wow.
Yeah. So she's studying with Dr. Hetrick.
So there's more money in that than astrophysics, isn't there?
I don't know yet. It's my second year of master. One more semester to go. Yeah.
Well, the data analysis is what you need to find a planet 9,
Yeah,
right?
yeah, that's the reason why that I choose data science too. Like I want to know more how to models and things like that. Use algorithms to how it works, you know.
It's exciting.
Oh, real exciting.
Very
good.
Interesting, yeah.
Good.
Okay. Is there any business out there? Anyone need to bring up anything that we haven't talked about or haven't talked about enough?
I'd
Lovely.
be interested in asking Jeff what our upcoming programs are that he's got in store for us.
Okay, so next month we have an interesting program, and it sounds a little goofy, but it's the MUFON Mutual UFO Network, which, you know, at first I had some questions about, but at the same time, in discussing with the guy and reading his stuff, seems to be quite the objective researcher and more of a investigative point of view than a believer point of view. And either way, I'm fascinated to see what it's all about. A few years back, I gave a program to a UFO group, and I asked if they would give us one someday, and then I lost track of them. This is more of a national network thing. So I'm optimistic that it'll be interesting. So that will be our February program.
Sounds good, Jeff.
Very good. Well, excellent program tonight, Jeff. Thank you.
Yeah,
Good
I
job.
think this was pretty awesome. I
Fantastic.
saw him last month at
Tri-Valley.
Don Mackolt and I were both at that meeting last month with the Tri-Valley Club, and it was very fascinating, and I'm really glad he was able to do one for us.
So I'll put in another plug for vice presidents. It's probably one of the hardest jobs in the executive board. And to consistently find good speakers like Fred did, and now Jeff is holding true to form. This is great because this is what really makes our club meetings worthwhile. We're actually informative, gives us a different point of view on things, and makes us come together. So I'm really
You know,
proud
this
of
is
all
only
of you.
1 month down. We've got 11 more months to go.
Yeah, but I have faith in you, Jeff.
I'm glad you do.
And if not, we're going to shoot you. No, I'm not kidding. Okay, I don't have anything else going on. If anyone has anything to say, we can kill a few minutes. If not, we'll close the meeting.
Don Mackolt, I see you're here and was also at the Tri-Valley meeting. Anything you wanted to comment on these two meetings about this Dr. Batygin?
Batygin.
No, interesting stuff though on searching for the people who are searching for asteroids and comets that might one day hit us may be the ones who will find Planet 9. I don't know how deep you have to go to get Planet 9, but they get down to about 21st or 22nd magnitude. And they do cover pretty much the whole sky, including where the Milky Way is.
Well, if it is a
software to pick up moving objects.
Well, if this thing is 3 Earth diameters and has an albedo of 60%, and with enough survey work, maybe in our lifetime it'll pop in.
Yeah, I expect if it's out there, it will probably be found within the next 10 or 15 years.
Well, didn't he say, or was it that the Planet 9 came into the solar system in its orbit, or was that the other KBOs that he's using for modeling that come inside the solar system?
I don't know.
I might be wrong, but I think what he was saying was some of the other KBOs, when they come into the solar system around the orbit of Neptune, then they can be like re-injected or in different ways in the solar system. Yep, yeah, exactly.
They can also be tossed out and thrown off of our hedosphere. So I don't know if you guys know this or not, but if you look at Eric, you can see that he's got a job at the James Webb Space Telescope building.
Depending on you, Eric.
I muted.
It's all right.
Go ahead.
Now, what's it like, Eric? It looks like fun.
I'm not really there, guys. I'm not really there.
Well, what's the latest news on James Webb? I heard that the solar panel is deployed well, and that they were unfolding the mirror now.
No, it's the James Webb is fully deployed now, and they're doing mirror steering. So they're really just doing mirror alignment at this point.
It's
so
about
exciting.
2/3 of the way, 3/4 of the way there.
Yeah.
It's pretty cool.
Yeah, I follow a YouTube channel that does continuous updates that NASA supports, and yeah, they rolled out the port side and then the starboard side, and that was it. Now they're just collimating the instrument, and they'll be doing that for the next 6 months, really.
So first light sometime in the fall, Mark?
I think so. Mhm. Well, actually, maybe slightly sooner. I think they were talking about June or July, I think.
So many single points of failure on that thing.
I think they've got a lot of them behind them now, which is,
Yeah.
you know, yeah, it's tense.
Well, okay. I don't have anything to say. So if anyone has anything to say, say it. Otherwise, time to close the meeting, ladies and gentlemen. Okay.
Very good.
All right.
Thank you all.
Okay, so let's go ahead. It looks like that wraps it up. Is there a motion to adjourn? Jerry, say yes. Jerry, say yes.
I move we adjourn this meeting.
There's a second.
Again,
I think the most adjourned button is that red one down. at the
Okay, the red
bottom
one
there.
down there. Aye, say aye.
Aye.
No, okay.
See you, everybody.
Meeting's
Good to see
adjourned. Good
y'all.
night,
All right.
everyone.
Good night, you all. Bye-bye.
Bye.
Bye.